All right. Okay, so let's jump in. Just a little bit about me before we get started, guys. So I graduated from Sydney Grammar School last year in 2020. These days I study Bachelor of Science at Sydney University. So I don't do as much chemistry these days, but I study financial mathematics and economics myself. So still sort of in the quantitative area a bit, and I'm here to help. So throughout the lecture, if you've got any questions, please feel free to type them into the chat. So you guys won't be able to see the questions that you type, I don't think, but I'll be able to see them. So if you have any questions along the way, just feel free to type them in. And we'll have a bit of question time between each section. So hopefully I'll be able to get around to answering a lot of them. Okay, so a bit of an overview before we start. So what's the recipe for success in a chemistry exam? So I just wanted to put in these band 6 and band 5 estimated raw marks for you guys. So I just wanted to show that basically because of how well chemistry scales, the raw mark that you need to do really well on a chemistry exam isn't as high as you might think. So a raw mark of 82 out of 100 in the actual exam, so that means you've got 18 questions wrong, that's going to scale up to a 90 at least. And often it's a bit higher than this as well. So this is like my estimate. I think that if you get 82 out of 100, you could even go as high as 91 or 92. And what I want to show by this is just that when you're doing a chemistry exam, your focus should really be on getting 100% in all the questions that you can get right. So because it's a tough exam, I think that for the majority of students who are probably aiming to get band 6, band 5, that sort of thing, what you really want to focus on in an exam is getting all the questions that you can do completely correct. And then after you're sure about that, then getting into some harder questions. So I don't want any of you guys to get stuck on harder questions in an exam. Because what I'm saying here is if you let a couple of marks here and there go in harder questions, that's fine, as long as you're getting everything else correct. Saying that though, this lecture will be focusing a bit more on the harder style questions. So the idea is by this point, we're hoping that you guys are sort of getting really accurate in your exams, but this is going to sort of help you guys approach some harder questions that you might not have seen before. Okay, so this is just a slight sort of a summary of what we're going to be talking about today. So all the different question types that we're going to be looking at. And this is an exam breakdown. So just in case any of you guys aren't too familiar with what an HSC chemistry exam looks like, just in case any of your trials were different, you're going to have a multiple choice section, which is going to take about 30 to 45 minutes, a short answer section. And then so you can expect that some of those tougher questions that we're talking about are going to come towards the end of the multi-choice and then at the end of the short answer. So once again, when you're doing an HSC chemistry exam, I want your first priority to be making sure that you're getting everything correct that you can, because at the end of the day, if you get all the questions that you can do completely correct, you're going to do really well. And then hopefully this lecture will provide you with some questions you might not have seen before, so that if any of this sort of stuff does come up in the exam, then you can get that correct too. All right, so into our first question. So this is a question from the HSC exam last year. I'm just going to get my iPad online here. So I'm going to be annotating these slides as we go. And I apologize if any of you guys haven't done the HSC exam from last year. Maybe you're saving it. But I promise I won't be doing too many HSC questions from past years. I will be leaving those for you guys to do yourselves. However, these questions that I will be covering from the HSC, these are tough ones that I think that you'll probably need help with anyway. All right, yeah. So as I was talking to Emma about before, there's going to be some little multiple choice sections that you guys can use. So have a look at this question for me and see if you can have a shot at getting an answer. So I'll give you a minute or two to read through it. And then I'll go through the solution once everyone's had a chance to read it. Okay, awesome. So hopefully by this point, everyone's had a chance to vote. Emma, is there any way that I can see the results?
Yeah, we're just still getting a couple answers, so maybe give them another 10 or so seconds.
Easy, too easy.
Okay, I'll share the results with you now.
Awesome. Okay, so bit of a spread. So we've got people thinking A, B, C, and D. So D was the most popular answer. Let's go through it. All right, so this is an equilibrium question, obviously. And I think one of the big challenges for challenges in equilibrium questions is actually getting down the right equation for the question. So as we know in chemistry, it's really important to get down an equation which is describing what's happening. But in this particular question, we've got copper sulfate flying around. We've also got sodium hydroxide flying around. So in a lot of equilibrium questions, the challenge is actually writing down the right equation, which is going to help you answer the question. So in this particular one, we want to write down an equilibrium expression between solid copper sulfate and copper ions, as well as sulfate ions. And what I mean, like by what I was saying before, is it could be like a common mistake to go like copper sulfate plus sodium hydroxide, because sodium hydroxide is being added to the solution. But what we're actually doing in this question is analyzing this equilibrium and not this addition between these two species. Okay, so we're going to start by looking at this equilibrium. And if you guys have done pracs at school, you know that aqueous copper and also copper in crystals is what turns a solution blue. So in this question, what determines how blue the solution is actually the amount of these guys here, the amount of copper. So with this equilibrium, what we want to determine is whether adding sodium hydroxide is going to affect the amount of copper 2+ ions, because the amount of copper 2+ ions are what's going to determine this blue color. All right, so when we add sodium hydroxide, what's actually going to happen is some of these copper ions are going to be precipitated out of the solution. And the reason for that is because copper hydroxide is actually insoluble. So by adding sodium hydroxide to the beaker, what's actually happening is we have this equilibrium which is established here. And some of these copper ions are actually going to react with the hydroxide that we're adding into the solution and therefore precipitate out. So adding the sodium hydroxide in this question is actually the same as taking copper ions out of this equilibrium that we've drawn here. And then the sodium that we're adding is just a spectator ion, which isn't doing much. So what's going to happen here is that the color of the solution is actually going to fade. So it's either going to be B or D, because we're going to have less of those aqueous copper ions. And now we just need to work out what's going to happen to the mass of copper sulfate. And we know that in an equilibrium, if we take out some of the products, which is once again sort of happening here because they're precipitating out with that copper hydroxide, then the amount of reactants is going to decrease. So therefore, it's going to be D. All right, so good job if you guys got that correct. So a couple of pieces of knowledge to take away here. The first thing to take away is that aqueous copper turns a solution blue. And also in an equilibrium question, it's really important to get down the right equation, which is actually describing like the main part of the question. And then other stuff that you're adding to a solution, you can almost think about it as sort of affecting that equilibrium that you've already written down. All right. So if there's any questions about that, I'll get to them at the end of this section. But yeah, as I was saying before, we're just going to move through a bunch of harder questions. So I'll move on to the next one now. All right. So this is the next question. So we're adding lead nitrate to sodium chloride, and we're determining if a precipitate will form. So once again, in this question, we want to start by writing down the right equilibrium expression. So if a precipitate's going to form, the first thing we got to work out here is what precipitate is actually going to form. So looking at the two things that we're adding, we're going to get the lead we as a value from nitrate. It has
Hey guys, sorry about that. Jackson has just messaged saying he's got an issue with his Wi-Fi, but he should be back online in a couple seconds. If you have any questions, just put them in the Q&A and we'll get to them when he's back on the line. Shouldn't take too long. Hey Jackson, are you back?
Hi guys, sorry about that. You have to bear with me. Sometimes my Wi-Fi just cuts out a little bit. All right, let's get back into it. Here we go. All right. Okay, so back to the question. So before it cut out, I was just saying that the first step in this one is to work out what solid is actually going to form, like what's the precipitate going to be here. And we have two options. We could either have like lead chloride being a precipitate, or we could have sodium nitrate being a precipitate, like based on the two reactants that we're given. And then this guy is going to be our solid because sodium nitrate is soluble. All right, so once again in this question, we're going to ignore the spectator ion. So ignoring spectator ions in an equilibrium question is a common sort of trick in harder questions. And instead of sort of considering every ion that's floating around this question, we're just going to consider the solid lead chloride, which is going to be this precipitate that we're talking about in the question. So let's write an equilibrium expression for that. So you have lead chloride goes to lead 2 plus chlorine minus, and then we're going to have to put our 2 there to balance. Okay, and so from here, we're going to, we need to determine if the precipitate is going to form. So this calls on us to understand how to use Q. So Q, for those of you who might not be too sure, Q is like K in that it gives the concentration of the products over the concentration of reactants. However, Q is at any point like within a solution. So Q just measures the concentration of the products over the concentration of the reactants, like depending on the specific species flying around. And Q doesn't necessarily have to be at equilibrium. So that's the important distinction between Q and K. Q is just this ratio at any time, whereas K is specifically at equilibrium. Okay, and the other important thing is that if Q is greater than K, then a precipitate is going to form. So what we want to do in this question is we want to work out whether this ratio of the concentration between products and reactants is going to be bigger than the ratio between products and reactants at equilibrium. So to do that, we're going to go Q, like our specific Q expression for this reaction is going to be the concentration of lead times the concentration of chlorine squared. And we square it because we have this coefficient of 2. Additionally, for our Q expression, we're not going to include the concentration of the reactants in this case. And the reason for that is because we don't include solids within our Q or K equations. So although Q is the concentration of products over the concentration of reactants, if your only reactant is a solid, you're just going to leave the denominator as 1 in this ratio. Okay, so from here, it's just a matter of substituting in the values that we've got. So to work out the concentration of lead, we've got to be careful. So we're told that the concentration of lead that we're adding here is 0.1 moles per liter. However, a common trick is that although our concentration here is 0.1 mole per liter, we're actually adding in another solution here. So the concentration of lead is going to change after you've poured these two things together. So although we're originally 0.1, we're going to have to work out the new concentration of lead ions once we've added the sodium chloride as well. So to do that, I'm going to use concentration equals moles over volume. And if we have a certain amount of lead here, we can work out the moles of lead that we're initially putting in using the concentration and volume of this initial solution. So we're going to say that we initially have a certain amount of lead, then we're adding another solution. So once we've added that other solution, the moles of lead aren't going to change because we're not adding any extra lead. So this moles in here, we can work out from these two concentrations, like this concentration volume from up here. And then our volume, we're going to work out using the volume of the two solutions that we've added together. So we're going to add 0.15 to 0.1 because those are our volumes. And like as usual, we're going to work in liters instead of milliliters. So we're going to do 0.15 plus 0.1, which is 0.25. So that's going to equal 0.15 times 0.1 over 0.25. So once again, I've gotten this 0.15 times 0.1 because I'm working out the moles of lead that we're going to have in this solution once we've pulled the two stuff together. All right, and if I put that into my calculator quickly, we're going to get 0.06. And then we're going to do a similar process for chlorine. So for chlorine, I'm going to work out the moles that we had in the initial solution before we added other stuff. I did the same thing. Sorry. Concentration equals moles over volume. So our concentration is going to be 0.1 times 0.2. So just the same thing as last time over 0.1 plus 0.15. So I'll put that into my calculator. 0.1 times 0.2, 0.25, and that's 0.08. So we're going to times that by 0.08 squared because that's the result of this guy. Okay, and if we put that into our calculator, we multiply 0.06 times 0.08 squared, we're going to get 3.84 times 10 to the negative 4. All right, and as I was saying at the start of the question, we've got to compare this Q we've got to compare that to K, and if Q is bigger, then we're going to have a precipitate form. And we're going to get our K value from the formula sheet actually. So looking at the formula sheet, they give you solubility constants for lots of common precipitates. So I'm looking for lead chloride at the moment. And lead chloride has a K value of 1.7 times 10 to the negative 5. So I'll put that in. So we know K equals 1.7 times 10 to the negative 5. And therefore, Q is bigger than K and a precipitate's going to form. All right. So once again, if you guys have any questions about that, feel free to type in the chat and I'll come back around to it once we get to question time. All right, cool. So on to the next question. This is another one that you guys can engage with. So take a minute or two to think about what you reckon the solution would be and then enter it into a poll. If Emma, you could take care of that for me.
Yeah, I'm just getting it up now.
Lovely, thank you.
We'll give you about another 10 or so seconds. Okay, about 50% of people have responded now, so I'll end the poll and share the results.
Great. Okay, so about half the people thought it was B, some others thought it was C or D. All right, so let me go through it now. Here we go. All right, so if, so we're asking whether the K of the reaction decreases when the temperature is increased. All right, so once again, sorry, K equals the concentration of products over the concentration of reactants. So if we know that the K of the reaction decreases, then what we're actually saying is that the concentration of the reactants relative to the products increases. So in other words, what the question is telling us is that the concentration of the reactants is going to increase and the concentration of the products is going to decrease. So what I'm going to do is I'm just going to draw out like a sort of pretend equilibrium, if you like. And what we've got to work out is whether the enthalpy change is negative or positive based on this. So what I'm going to do is I'm actually going to guess and check. So I'm going to say, well, let's assume that the enthalpy change of this reaction is negative. And then I'm going to think about whether or not that actually works, and whether or not it works is going to determine our answer. Okay, so if the enthalpy change of a particular reaction is negative, then decreasing the temperature, and so also if the enthalpy change is negative, that means we're exothermic. So we can think about heat as a product of this reaction, because if the enthalpy change is negative, then we're releasing heat. So once again, I'm just sort of assuming that the enthalpy change is negative, and then we're going to see whether that leads us to a correct place. So if the enthalpy change is negative, then heat is essentially a product. So decreasing the heat would actually increase the concentration of the products relative to the concentration of the reactants. Because we know, like, we can view heat as just a product. And we know that in an equilibrium system, if we take out a reactant, then the concentration of the other, if we take out a product, the concentration of the other product is going to increase, and the concentration of the reactants are going to decrease. But that's actually not what we want from this question. We want to know, we want the reactants to decrease and the products increase. So we know that our assumption that we're exothermic is incorrect. And in other words, B is the correct answer. And we actually are endothermic in this reaction. Okay, so a big thing that I'd love you guys to take away from this question is this trick of using heat as a product of a reaction. And I just think it's a really neat way to work out changes in equilibrium systems. So it's not actually like a valid thing. Like if you're asked to explain like why temperature is affecting equilibrium in a particular way, you can't just say heat is a product of the reaction. But in terms of predicting changes to an equilibrium system, it's really useful to view heat as a product of the reaction in exothermic reactions, and to view heat as a reactant in the equilibrium system for endothermic reactions. And because in endothermic reactions, you're taking in heat, right? So you can sort of think about heat as a reactant that way. Okay, so Emma, that's, are we out of time for the first section?
You can keep going if you want, it's up to you.
Okay, I might just take a look at the questions quickly. I might, sorry, I'm a bit lost here. Do we have any questions that look like they could be good to answer, or
We haven't got anything coming through yet, but if the attendees want to put stuff up, we'll be happy to answer them.
Yeah. So if you guys have any questions about the last couple that I've gone through, feel free to shoot them through. Otherwise, I'll just like move on to the next one.
Also, if you have any like exam technique sort of questions. So we've got one here saying that they're a little bit confused as they thought it was heat is increasing, so the reactions will increase if the reaction is exothermic.
They thought that temperature is increased. Yeah, that is true actually. Yeah, so heat is increased. Yeah, sorry, they've actually called me up there. That's true. Heat, I was assuming before that heat was decreased, the temperature was decreased, but temperature actually is increased in the question. So they're right. Sorry about that, guys. So you can think about the question in the same way. However, at this last stage, you do, like, temperature is increased. I was assuming that it was decreased. So if temperature is increased, then we can think about the equilibrium system as sort of like adding in a product, and that would decrease the concentration of the product relative to reactants. So for that reason, it actually is C. Sorry about that, guys. Yeah, so the question does read that temperature is increased, not decreased. So thanks for that. And please feel free to pick me up on that stuff. I will make another small error like that, I'm sure, as we go through. Is there anything else, or?
We've got another question saying, in the second question we did, why did we put 1 plus 0.15 in the volume when working out the concentration of chloride ions? Sorry if that doesn't make sense. I'm just confused with the working out.
No, that does make sense. So if we go back to the last question, sorry, I'm just, here we go. Okay, so if we go back to this one, so for the volume, I did 0.1 plus 0.15 because we know that concentration is moles over volume. And when we add these two solutions together, the new volume of the solution is going to be 0.15 plus 0.1 because we're adding 150 milliliter solution to 100 milliliter solution. So because we're trying to work out the concentration in the new solution once they've been added together. And that's why I use the volume as sort of the entire combined thing. I hope that answers your question.
And the last question we have is just in the KSP question, do we have to multiply the chloride concentration by 2 since the ratio is 1 to 2?
Do you have to multiply? No, you don't. That's a good question, but you don't. So if you have an equation, say we have A goes to like 2B, and so if we're considering this sort of equilibrium system, then our K would equal the concentration of B squared over the concentration of A. So I think our person is asking, like, once we work out the concentration of B in the solution, do I then multiply it by 2 because of this coefficient here? And it's a good question, but the answer is actually no, you don't. You just keep the concentration as what it is and you just square it. So yeah, hopefully that answers the question. Awesome. Is that, if that's all, I might move on to the next section. Might get on to our acids and bases.
Yeah, awesome.
Okay, cool. So onto some acids and bases. So I'll give you guys a minute to look at this one and get an answer down. And you can chuck it into a poll as well.
I'll just get that up now.
Thank you.
We'll give it about another 10 or so seconds.
All right. All right. So D was the most popular answer, which is correct. D is correct. And we did have a fair few people thinking A, B, or C. So we'll run through it quickly. So just in terms of like rote learning how to do these questions, it is good to remember that like when we're adding a weak base to a strong acid, or like if we're doing a weak and strong titration, this little bit in the middle of this curve here, which is characteristic of like a weak plus strong acid and base, the middle of this bit is actually where the solution is going to act as a buffer the best. So that's why 9 is the correct answer. So that's what you should just remember. But in terms of explaining why that's the case, let's just remember what makes a buffer solution. So a buffer solution is when you have equal concentrations of a weak acid and its conjugate base in a solution together. The other, so we have three things. You need equal concentrations, you need a weak acid, and you also need its conjugate base. All right, so if that's what it takes to make a buffer solution, let's talk about why it is that a buffer actually occurs here. And like the first thing to say is that buffers resist change in pH, right? So if we look at how this curve is actually working, we can see that although we're adding lots of stuff here, the pH is staying relatively sort of flat, right? So in terms of like, we know that a buffer sort of resists changes in pH. So just like looking at this diagram, it looks like our buffer is going to be around here because this is the stage where we're resisting changes in pH. Additionally, at this stage here, we're going to have added a little bit of acid, and we're also going to have our weak base there too. So our weak base is going to still be floating around the solution. In other words, we're still going to have more of our weak base than our strong acid because we know that this is the equivalence point. This is where we have equal molar ratios of base and acid. So at this point, we're still going to have more base than acid. And so what that means is that we're going to have that base and its conjugate acid flying around there. And because at this stage, we're going to have a strong acid. And we know that if we have an overwhelmingly strong solution with acid, you're not going to get a buffer because you need a weak acid and its conjugate base. Okay. In terms of just like doing these questions, though, it's a great thing to remember just for multis that this is the place where you're going to get an effective buffer solution. Okay, let's move on to the next one. Here we go. Okay, so I want to look at, this is called a back titration question. So students often find this one tough because there's so many steps to it. So I'll give you a couple of minutes just to read through it because it's quite a long one. I don't think you guys will be able to participate as such in this one, but please just read through it for me for a minute and see if you can get your head around the question. And then we'll talk about how you can sort of go about solving these hard, like longer style questions. How are we going, Emma?
I think just give it another like 10 or so seconds for people to just finish up.
Lovely.
Okay, yeah, go for it.
Cool. Okay, so I want to talk about how to do longer chemistry questions where there's a lot of sort of reading. Because it can be really easy to get lost in questions where there's a lot of steps, right? Like something's diluted, then it's taken away, then it's titrated. There's a lot going on. So this question is really nice because it actually lays it out in terms of steps. But I think that even if it doesn't do that, in most of these back titration questions or like longer questions, it's useful to sort of put like step 1, step 2, step 3, step 4, like that anyway, just so you can sort of get it straight in your mind exactly what's going on. So that's the first tip I have for longer questions. The second tip I have, which I think is really helpful, is to work from step 4 back to step 1. And we'll see why in a second. So let's just start by doing 30 part A. So 30 part A is just a simple sort of question. It's just asking what's the moles of NaOH in step 2. So it's just asking us to say moles equals concentration times volume, which in this case is 0.05 times 1, which is 0.05. So part A is relatively straightforward, but part B is the really tough one. Okay, so as I was saying, what we're going to do is we're going to start at the end. We're going to start at step 4. We're going to work backwards. All right. And just to sort of, so that everyone understands what's happening here, what we're doing is we have a certain amount of something. We're reacting it with sodium hydroxide, which is in excess. So the way this question is going to work is this is what we're trying to like find, if you like. This is the NaOH. And what's happening is that a certain amount of this is reacting with this, leaving some leftover NaOH. And what we're doing is we're analyzing how much leftover NaOH there is. We also are going to, like, we also know from part A how much NaOH there was in the beginning. So the way this question is going to work is if we subtract the leftover NaOH from how much we had at the beginning, that must be how much actually reacted with the dry ice. In other words, the thing that we're trying to find. So that's sort of the long-term method with this question. But as I was saying, let's sort of start by working back from the end. So let's just start at step 4. Think really reductively, start at step 4 and work backwards. So we're saying that sodium hydroxide was titrated against a 1 mole per liter solution of hydrochloric acid. The average volume of HCl used was 27.6 milliliters. So what we know, therefore, is the moles of sodium hydroxide like at the equivalence point. So we know that it takes 1 times 0.0276. So I'm using moles equals concentration times volume here. And I'm saying that at the equivalence point of a titration, which is what's happening in step 4, we're going to have equal molar ratios of sodium hydroxide and also hydrochloric acid. So if we know how many moles of hydrochloric acid there were at the equivalence point, then we also know how many moles of sodium hydroxide there were. So I'm saying that the moles of sodium hydroxide, therefore, is 0.0276. Cool. So if I draw my little diagram up again, so we have our thing we're trying to find, we have NaOH, and we also have the excess. What we've actually found here is how many moles of NaOH there were in excess after reacting with the thing that we're trying to find. So we know that this guy had 0.05 moles, like the whole NaOH. We know that after reacting with the dry ice, there was 0.0276 moles left. So that must mean that if we subtract 0.0276 from 0.5, then we're going to get the amount of moles of dry ice there was. So I'm going to put that into my calculator. I'm going to go 0.05 minus 0.0276. I'm going to get 0.0224. All right, great. Actually, no, sorry, that's a slight mistake. And the reason for that is because we actually have a 2-to-1 molar ratio here of sodium hydroxide. So sodium hydroxide to carbon dioxide, we actually have twice as much sodium hydroxide to react with the carbon dioxide. So what we know is that there was 0.0276 in excess, 0.05 sodium hydroxide at the start. So we would have 0.0224 moles, which is just this minus this, of sodium hydroxide reacting with carbon dioxide. But that doesn't necessarily mean that we have 0.0224 moles of carbon dioxide. It actually means that we have that divided by 2 moles of carbon dioxide. Because although this number is definitely how much sodium hydroxide reacted, for every mole of sodium hydroxide, only half a mole of carbon dioxide is actually taken up. So it's almost like a bit of a limiting reagents question. So we're going to divide this by 2 to find that there's 0.0112 moles of carbon dioxide that was actually reacted. So at this point, what we know, which is really important, is that we have 0.0112 moles of carbon dioxide. Great. So we're trying to calculate the percentage purity by mass of the batch of dry ice though. So it makes sense to convert this moles into mass. So we're going to use mass equals moles times molar mass. Moles times molar mass. So we're going to multiply this number by the molar mass of carbon dioxide. So we're going to do, we're going to go 0.0112 times the molar mass of carbon dioxide, which is, I'm just going to get my periodic table out. So carbon is 12.01 and oxygen is 16. So we're going to do 12.01 plus 2 times 16. So that's the molar mass of carbon dioxide. And we're going to put that into a calculator. And we'll get 12.01 plus 2 times 16. We're going to get 0.49 grams. So what we know is that in the contaminated batch of dry ice, there was actually 0.49 grams of carbon dioxide. So to then find the percentage purity, what we're going to do is we're just going to divide 0.49 by the mass of the contaminated dry ice. So we're going to do 0.49 over 0.616, and we will get 80%. Awesome. So that's how we do this question. So once again, in these longer questions, what you want to do is you want to work backwards from the end, and you also want to be really clear in your head about what's happening at each step. We're going to go through another longer one like this a bit later. Okay, cool. Let's move on to the next one. As I was saying before, we'll get 20 questions later on. Okay, let's look at this question. So guys, just take a minute or two to have a look at it and get your answers in.
Someone's asked a question about whether we're going to go through extended response questions later.
I actually don't have any planned specifically, but we will have question times at the end of this. So if you'd like to type in a type of extended response style question that you'd really like to look at, I'm happy to go through that for a couple of minutes in question time for sure. So are you talking about like biofuels perhaps? I can also go through, you're saying some easy methods to answer them. I can definitely go over that for a couple of minutes. But so what sort of longer response style questions trouble you? Is it more like how to do a reaction, or is it like contrast biofuels and fossil fuels? Yeah, I'd love to hear if you want to type to the chat what sort of questions you'd like to look at. I'd love to hear. Is that a response? Okay, yeah, okay, sure. So in question time, I'll definitely go over the structure we follow based on marks. Sure. So in about 5 or 10 minutes, I think we've got question time, and I'll go through that then. So stay tuned. Okay, so I'm going to go through this one now. So the overwhelming majority of people thought it was A. The answer is actually B to this one. And this is a really confusing question. Let's start, so answering this one, let's start by answering an easier question. How much, so let's say we have a strong acid and a weak acid, and then we have a strong base. So the question I want to ask you guys is, do you think that it will take more strong base to neutralize a weak acid, or will it take more strong base to neutralize a strong acid? And the answer is actually pretty confusing. The answer is that it's actually the same amount. So no matter whether an acid or a base is weak or strong, it's going to take the same amount of like the opposite thing. So if we have a strong acid or a weak acid, it's going to take the same amount of a strong base to neutralize them. And it's a surprising result. And the reason for it is because even though strong acids dissociate in solution more than weak acids, that's true. However, the OH ions that float around the solution, they actually have the capacity to ionize stuff by themselves, which is really important. So this is a common sort of idea in harder questions. So the thing to remember is that the thing to remember here is that strong acids and weak acids take the same amount of strong base to be neutralized. And that's because the OH minus ions are really good at ionizing stuff by themselves. So even though we have a weak acid, that OH is going to pull out the hydrogen from that weak acid by itself. All right, so as I can see in the chat there, that person's correct. The reason it's B is because it's triprotic. And this question also comes down to another important idea. So so I know like what we just talked about doesn't look like it might necessarily link to this question, but I'm going to all link it together in a sec. But I also want to talk about the fact that this is triprotic. So a triprotic acid, it dissociates like this. So we know phosphoric acid is a strong acid. It's going to go like this, H2PO4 minus. So once it's dissociated, we're left with this guy, right? But this guy is actually still an acid because it has the capacity to donate a proton. So in the solution, what's going to happen is we have this H3PO4 flying around. That's going to dissociate in this first step. But then the thing that it produces is also going to dissociate. So this guy's also going to act as an acid, and it's going to dissociate into H plus and PO4 2 minus. H plus and HPO4 2 minus. Yeah, and then this guy is also going to be an acid to some extent. So they're also going to donate some protons. So this idea of stuff this stuff sort of dissociating multiple times is also a really important idea. So like with this question, what we're saying is that all of these three are going to take the same amount of acids. They're going to take the same amount of bases to be titrated. Because it doesn't matter whether they're weak or strong. Weak or strong acids take the same amount of base to titrate them. So we're just left with H3PO4, and it does take more base to titrate H3PO4 because H3PO4 is essentially just like multiple acids all together, because it's gonna dissociate, and then it's gonna dissociate again, and then again. So we're gonna be left with a lot of acids floating around. So it's gonna take a lot more OH minus ions it's going to take a lot more OH minus ions to pull out all those 3 hydrogens. The thing to take away from this question is, as long as acids and bases have the same amount of, as long as strong acids and weak acids have the same amount of protons, it actually takes this, the same amount of base to neutralize them. Cool. Let's move on to the next question. Question time. Okay, cool. So I will go through now, just for a couple of minutes, how to answer some longer style questions, because I do have some tips on that. So longer style questions. The first thing I'd say is that the NESA booklets, they don't give you enough room. So if you just answer, say you get like a 6 marker, and you just fill up the space that they've provided you, it's actually unlikely that you're going to get 5 or 6. And that's the reason that they provide you with extra writing paper. So not that you should be trying to just like write as much as you can, but just in terms of like the level of depth that you need to answer questions, you'll actually find that most of the time, if you're writing about the correct stuff, you'll be going over the limit. So don't be afraid to go on to another writing page. And in your preparation, I definitely recommend practicing being really neat about that. Because if you're a marker in the HSC center, you don't want to have to flick around through pages, see all these asterisks and stuff. You just want to see it right there, right? So when you get to the end of your allotted writing space, just write a really clear note, rest of the question written on extra writing paper, and then label your booklets properly. Okay, so that's the first thing to say. The second thing to say is I think that you guys should be not afraid to use subheadings. So just for example, a really common question, longer style question, is explain the trends of boiling point. You can see in this graph. So for example, if we have a bunch of different organic substances, like this. So this might be this might be ethanol, this might be ethene, this might be an alcohol. This might be I don't know, well, yeah. And we have different types of organic substances, and this might be chain length. And this is boiling point. So I'm sure you guys know the sort of question that I'm talking about. And the common question is explain the trends that you see in this graph. What I'd do is I'd say subheading 1. So I'd say trend 1. I'd say the boiling points converge. And then I'd write a couple of lines about why that trend happens. Then I go trend 2, underline it. I go, the alcohol has a higher boiling point than just the hydrocarbons. And then trend 3 might be with greater chain length, we see higher boiling point. And you're going to have those subheadings. All right. Then the other, my final piece of advice, which is maybe my most important one, if I were you guys, I would collect some longer style questions and I would write practice solutions for them, and I'd send them to your teacher or a tutor to get them to mark them for you. Because what you'll find is that lots of the longer style questions come up over and over again. I'm sure if you guys have done a fair few trials by this point, you notice that the amount of questions which ask you contrast the environmental impacts of fossil fuels and biofuels. You've probably seen that sort of question 50 times, right? What you should do, you should write out a response. You should send it to your teacher, get feedback, and almost just rote learn it, you're rote learning an essay in English or something like that. And obviously, in English, you've got to tailor it to the question still, and you can't just spit out any response to any question. But I'm saying that you should have some bits and pieces that you can plug in here and there, and I think that'll really help you in the HSC. So So those are 3 tips I have for longer style questions. That's helpful. All right, so I'll move on to the next section. We don't have any more questions, do we, Emma?
I don't
I don't
think
think we have any
so.
more questions. Okay, too easy. Well, I might move on then. Okay, so on to our organic chemistry. So here's another multi. So I'll give you guys a couple of minutes and feel free to put in some solutions for me.
We'll give it another like 15 or so seconds just to get some more responses.
Cool. Awesome. So majority of responses were D, which is correct. A couple of B's and C's as well. Okay, so these polymer questions can be a bit tough. So I just wanted to go through this example. So the first step in these sorts of polymer questions is identifying where the repeating part of the polymer is. So in this one, the repeating part is this little bit here, right? You can see that this part just repeats over and over again. And because that part repeats over and over again, you can be pretty sure, and you can be certainly sure that that is where the monomer, like what the monomer is going to look like roughly. The second step in these ones is just sort of like think about, is it going to be an addition polymer or a condensation polymer? And in this one, it's going to be addition polymerization. And the way we know that is because we've just got that long repeating chain. Condensation polymers join like with like oxygen, like they look like esters, that sort of thing. Also, all the answers that we're given, like all of these look like addition polymers because the monomers that form addition polymers have that double bond in them. Okay, so then what we want to do is we've identified what the repeating chain is. So then you want to pick the one essentially that just looks the most like the repeating chain, and that's this one. So it's not C because there's no oxygens in the thing. It's also not B because the repeating part of the polymer just contains like this little bit, whereas this is too long for the repeating chain. And this is also wrong because for every repeated part, there's only one CH3 group, whereas this monomer would suggest there'd be two CH3 groups. So for that reason, the correct answer is D. Okay, on to the next one. All right, so for this question, you're actually required to know the formula for glucose and how glucose works in reactions. So this might seem like a sort of niche piece of knowledge. Understanding glucose is actually a really important part of this course. So so I'll give you guys some time, see if you can figure this one out. Also, see if you can work out what the actual reaction is in this question, because that's actually the hardest part, I reckon.
We haven't got any responses to the poll yet, so I'll take
Yeah.
it. People are still working.
I think this is actually a pretty tough one, so I might actually just get into it. I wouldn't be surprised if lots of people don't know how to approach it. So I might just start working actually. So the reason this one's so tough is because you have to know the equation which represents the fermentation of glucose. So people might have seen this in past papers and sort of skipped over it or thought this isn't something that you need to know, but I definitely say that this is a must-know piece of knowledge. So as you can see, this is a past HSC question, and I know this is from the old syllabus, but this question is definitely still applicable. So just for you guys' knowledge, glucose is C6H12O6. Definitely something to remember. And the fermentation process looks like this. So what it's going to produce is ethanol, H5OH. It's also going to produce carbon dioxide. All right, so we still need to balance this equation. So I'll do that now. So I'm going to put a 2 here, then a 2 here, and I'm pretty sure that that's balanced. Yeah. Okay, cool. So I would definitely, if I was you guys, write this down. You also need to write down the conditions for the fermentation reaction. So the conditions are 37.5 degrees Celsius, anaerobic environment, and also yeast. Okay, so if like in the HSC, they could definitely ask you just to write down. Thanks for that solution there. So in the HSC, they could definitely ask you just like write the fermentation equation for glucose. If you didn't write these reaction conditions, you wouldn't get the marks. You need to write all 3 to get the marks. You'd also need to balance it correctly and remember. You need to remember these species. Okay, so you might ask, like, why is it important? This equation is not only important just because they could ask it directly, but you should also be putting this equation in your responses, which contrast fossil fuels with biofuels. So I just want to do a bit of background here. So fossil fuels versus biofuels. This equation is important to talk about biofuels because it is the way in which ethanol is produced. Yeah. So if you and ethanol is like one of the main biofuels that you talk about, right? So if you're ever talking about biofuels, you want to talk about how it's produced. So you should also be using it in that situation. And like, by the way, another tip for longer style questions, they love equations. So if you're doing a longer style question and there's not many equations or diagrams, you're definitely not going to get full marks. So knowing these sorts of equations which fit nicely into longer style questions is also really helpful. All right, so let's get back to like the direct question. So for this one, we're asked what volume of carbon dioxide will be produced if 10.3 grams of glucose is fermented. Okay, so first let's work out the moles of glucose, which equals mass over molar mass, which equals 10.3 over the molar mass. So I just need to work out the molar mass. So it's going to be 12.01 times 6 plus 1.08 times 12 plus 6 times 16. And that's going to give us 180.156. So now we can work out the moles of glucose. So moles of glucose is going to be 10.3 divided by our answer from before. Okay, so we're going to have 0.05717 moles of glucose. Okay, so what that means is that the amount of moles of CO2 produced is going to be double that. So that's going to be that times 2, which is just 0.114345. Cool. And so from this stage, this is the second part of this question, which I really want to highlight. like I know the moles of carbon dioxide now, but how do I find the volume of gas produced? And you guys have actually got to use PV equals nRT from here, which is a piece of year 11 knowledge, which I'd say is a little, like, doesn't come up like heaps, but it's definitely something to know. Like, it does come up fairly regularly. So PV equals nRT, if you guys don't remember from year 11, is to do with gases. So what it says is if we know the pressure, the volume, the moles, and temperature of a particular gas, then we can sort of like work it all out. R is the gas constant, which is 8.314. It's on your formula sheet. And by the way, this formula is on your formula sheet. So with this question, we're asked to find the volume of carbon dioxide. So in the question, we're actually told what the pressure is. So 100 kilopascals. By the way, 100 like kilopascals is the right units to be using in this equation. Volume is what we're trying to find out. So I'm going to leave that as V. Our moles we've just worked out 0.114345. R is 8.314. Let me just double check that on the formula sheet. So on the formula sheet, it tells you the gas constant, which is 8.314. And then that's gonna, and then times temperature, which is 25 degrees. So the other common mistake here would be to use degrees, but remember your SI unit for temperature is Kelvin, not degrees. So you shouldn't really be working in degrees ever. All right, so 25, and you do plus 273.15 because you convert to Kelvin, like from degrees to Kelvin, by adding 273.15. All right, so if we solve this equation, then we're going to get the solution. So someone answered D, so I'll just check it for them just to make sure it's correct. 8.314, 25 plus 273.15 over 100. Okay, 2.3, yeah, so it's D. So good job to whoever answered that correctly. Okay. Awesome. So that's how you do that question. So 2 important pieces of knowledge there. This is the fermentation equation. Definitely get it down. Also, PV equals nRT. If you're ever sort of working with gases and they start telling you like temperature and pressure and stuff, it's probably going to be PV equals nRT. All right. Cool. Let's move on to the next one. Okay, so I'll give you guys some time to look through this question. And I'm just going to quickly find a charger for my laptop, but I'll be back in 2 minutes, guys. All right, so hopefully everyone's had a bit of a chance to go through this one. So this is, so someone just said this is such a common question, pops up at the very end of the paper. That's true. This sort of question does come up fairly regularly, but it's also a really tough one. So I'd love to go through with you guys. And I want to talk about just like a way to approach questions like this in general, which is you've got to sort of start by like having a group of organic compounds that something can be. And as you go through the question, you're going to slowly discount some of them. So what I mean by that is at the start, we're told that A is C5H10. So the common mistake here would just be to say that this is like, this is just butane. pentane, or pentane, sorry. That would be the common mistake. But in this question, we're not actually told that it's pentane, right? Like it could be anything. It could be 1 pentane. It could be 2 pentane. It could be also, it could look like this. It could look like this. Anything's possible, right? Actually, it couldn't look like this, but you get my point, right? So there's actually a lot of organic compounds that this could be. So let's start off with with these. One other one that I could think of that it could be would be this. All right, and I can't think of any others that it could be at this stage. And you'll notice that we're being really particular, right? Like the location of the double bond is really important for us. And what we're going to do from here is, as we're told more and more information, we're going to see which one it can or can't be. Okay, so we're reacting it with dilute H2SO4. So that's going to be a hydration reaction. So what that's going to mean is when we hydrate alkenes like this, we're going to add an OH group and a hydrogen across the double bond. So that's a bit of reaction pathways knowledge. And then the next stage, where we're obviously going to get an alcohol by adding dilute H2SO4 to an alkane. And what we're told here, this is a really important piece of information for us. We're told that this alcohol, when we add a strong oxidant to it, we're going to get no reaction. So the important piece of knowledge here is that when you have a tertiary alcohol, so in other words, you have an alcohol where the carbon that's bonded to the OH is also bonded to 3 other carbons. So something that sort of looks like this, where this OH group is bonded to a carbon that's bonded to 3 other carbons, this is called a tertiary alcohol. This can't be oxidized, this sort of stuff. So this is a really important piece of information for us because it discounts these 2 organic compounds that we've written down. Because no matter when we put in our OH, we're never going to get a 3rd degree or tertiary alcohol, which means that it can't be either of these 2. However, the other 2 that we've written down, when we add the OH to it, we actually could get a tertiary alcohol. And the reason is that for either of these 2 guys, you'll get you'll get tertiary alcohol. So another important piece of knowledge here is that when you add something and it has a double bond, the thing that you're adding gets added across the double bond. So what I mean is that we're adding OH and H here. Those are going to be added across the double bond. So let's say our answer was this guy. Then the 2 things that we get would be like this, OH, or we'd get this with the OH there. So these would be the 2 options if it was this guy, and I'm going to draw our other option over the other side of the paper. And by the way, this is the sort of working out that I think would be good to use in these sorts of questions. So I literally just write down what it would be, because if you're trying to pick between 2 organic compounds, just sort of write them both down, and then you'll get to a point where you can discount one of them. So if A was this guy, then our B and C would look like this, OH, or C, 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 OH. So you'll notice that we can get 2 different things by adding the same reagent, because when you add stuff across the double bond, whether the OH goes on one side of the double bond or the other side of the double bond is actually going to give us different stuff, right? Okay, so at this point we're pretty sure that it's one of these 2 things. And it makes sense, both of them would give us something that could be oxidized because these guys are 2nd degree alcohols, and secondary alcohols can be oxidized. So both of these are giving us something that can't be oxidized and something that can be. So we're on the right track. And then what we want to do is we want to work out what would happen in this last stage. So if we heat with concentrated H2SO4, then that's going to dehydrate the organic compounds that we're talking about. And by the way, this is a really important sort of detail. Concentrated H2SO4 versus dilute H2SO4, they do really different things. So concentrated H2SO4 dehydrates, whereas dilute H2SO4 hydrates. And if you're ever writing down like H2SO4, you do definitely need to put concentrated or dilute based on whether it's hydrating or dehydrating. Otherwise, you do risk not getting marks. So the classic example is like when you're doing an equation for esterification, you use concentrated H2SO4 because you're dehydrating. Okay. So let's continue our sort of method, which is like saying, well, it's either this or this. Let's go with both of them and see which one's wrong. So if it was this guy on the left, then if we add concentrated H2SO4 to these two guys, then the two options that we could get from this are we could get C, 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 C. We could get the double bond there, or we could get can I run up here? No. Or I could get this. So sorry, this one's getting a little bit messy, but yeah. So those are the two options that we get from this, and then this guy could either give us this C, like this, or it could give us, it could also give us this, because once again, like the things are coming across from like the double bond. So C, 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 double bond C. Okay, and at this stage, sorry, it's really hard to see this guy that I've written down because of the thing. So I'll redraw it. I'll redraw it up here. So these are the two from there. And C, 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 C. Okay. So what you'll notice is that this guy does fit the bill. So look, we're saying if this is A, then we're sort of getting stuff which makes sense, because by the final stage, you'll notice that in the final stage, like heating either B or D. So this is, yeah, so this is D, this is B. Like they need to both give the same thing and then both give different things. So like that makes sense because like these two guys are the same. So this would be A and this would be E and F. So let's, so we can be sure that this is the correct answer because we get to something which is true. And then for the other one, what you'll find is if we work with these two guys, we're going to get like the two compounds that these guys can produce, they're not going to produce something that's similar. And that's why this is the answer. Like all the compounds that we're getting on this side of the page are going to be correct, whereas these aren't. So sorry that the working has gotten really messy at this stage. But the big thing that I want you to take away from this is that you can't be too you can't make any assumptions with these organic chemistry questions. Like the other important piece of information is that stuff gets added across double bonds. And also that this sort of method of like seeing where it would go based on like things that we're not sure about is a really important one. We're going to see it again when we later look at some like CNMR, HNMR, like organic spectroscopy questions. This is a similar method that we'll use for that. Okay, so hopefully that makes sense. Please send any questions if you guys aren't sure. And I just want to move on to this next one. And that's Oops, sorry.
We'll give it another couple of seconds and just see. We've only got one response so far.
Okay, fair enough. Okay, cool. So just one response, someone thought B. So let's go through it. So we've got this monomer and we're going to turn it into a polymer. And we're told that the polymer has this molar mass. Okay, and the important thing to realize with this question is that a polymer is just this repeated over and over again, right? And when we add all these monomers together in addition polymerization, nothing like when we add two polymers together, it's just those two polymers, right? Like we're not losing water like we are in condensation polymerization. We're not getting any more atoms. So what that means is because we just have these monomers repeating over and over, and it's just them, the percentage by mass of carbon in this monomer is going to be the same as the percentage by mass of carbon in the entire polymer. And that's the important realization. What that means for us is if we can find out the percentage by mass of this, then of carbon, then we can find the percentage mass of carbon in the entire polymer and therefore work out the number of carbon atoms. All right, so let's do it. The percentage by mass of carbon in this, we're going to add up, we're going to go like 12.01 molar mass of carbon times 3, because there's 3 carbons, over the entire molar mass, which is 12.01 times 3 plus 1.008 times 6, because there's 6 hydrogens. Okay, cool. So that's going to give us the percentage by mass of carbon in the monomer and also the polymer. So that's going to give us 12.01 times 3 over 12.01 times 3 plus 1.008 times 6. All right, so that's 0.856. So roughly 86% of the mass is carbon. Cool. So what that means is that if this is the molar mass of the entire polymer, we know that 86% of it roughly is going to be carbon. So in other words, the molar mass, or like the moles of carbon in the entire polymer is going to be 0.856 times 1.05 times 10 to the 5. So that's going to give us the moles of carbon in the entire polymer. So I'm going to multiply that 1.05 times 10 to the 5. And that's going to give us, it's going to give us 908. So yeah, so this is the mass of carbon in the entire thing. Yeah, so this is the mass of carbon in the entire polymer, because we know that 86% of it is carbon. So we can work out the moles. So mole equals mass over molar mass. So the moles of carbon, therefore, is going to be 908 divided by 12.01, which is 7486. Okay, and with this number, we've got to use Avogadro's number. So Avogadro's number is the amount of atoms that are in 1 mole. So if we know how many moles we have, then we know how many atoms. So sorry, let me just go over this working one more time. So we've found the percentage by mass of carbon. So we know that there's 89,908 grams of carbon in 1 mole based on this guy. So if we have, so we found the amount of moles. Sorry guys, I'm blanking on how to do this question. Give me 2 seconds to see if I can remember. Because where I'm going with this is if we can find the amount of moles of carbon, then we can multiply it by 6.02 times 10 to the 23, which is Avogadro's number. So if we know the amount of moles of something, we can find the amount of atoms, which is what we're after. So let me just go through and see where my mistake is. Feel free to send it to the chat if it's blaring. Give me 1 minute. Okay, so in this question, I don't know, that's not right. Grams per mole. Okay, so my mistake is in this question, we're told that, we're told the mass of the polymer. So we're told that there's 1.05 times 10 to the 5 grams if we have 1 mole of the polymer. In other words, if we have 1 mole, so a mole is just a certain amount of things. So if we have a mole of polymers, then we have 6.02 times 10 to the 23, which is Avogadro's number, of these long polymer chains. So what we're told is that if we have 6.02 times 10 to the 23, if we have 6.02 times 10 to the 23 of these guys, then they weigh 1.05 times 10 to the 5 grams. So what that means is that if we only have 1 of these guys, then they're going to weigh 6.02 times 10 to the 23 times 10 to the 23 over, they're going to weigh, 1.05 times 10 to the 5 over 6.02 times 10 to the 23. So I'll go over that again. So we know how many grams 1 mole of the polymers weigh. So in other words, we have, 6.02 times 10 to the 23 polymers. This is how much that weighs. So if we just want to know how much 1 of the chains weigh, then we can divide the mass of a mole of them by how many there are. So that's going to give us, that number is 1.05 times 10 to the 5, 6.02 times 10 to the 23. And that's 1.74 times 10 to the negative 19. So this tells us that this is the weight of 1 polymer chain. And once again, we know that 1 polymer chain, 86% of the mass is carbon. So now we're going to multiply this guy, 1.74 times 10 to the negative 19, by 0.856 to find the mass of carbon in 1 chain, times 0.856. So we know that the mass of carbon in 1 chain is 1.493 times 10 to the negative 19. And then, so we can work out the moles of carbon this way. So moles equals mass over molar mass. So I can say the moles of carbon, so I'm going to start working over here now. Moles of carbon is going to be the mass, which is 1.493 times 10 to the negative 19, over the molar mass of carbon, which is 12.01. So that's going to be 1.24 times 10 to the negative 20. And then once again, if we know how many moles of carbon there are, then we can times that by Avogadro's number to find how many actual atoms there are. So if I'm going to multiply that number by 6.02 times 10 to the 23, we get that C is the correct solution. Okay, so I'm just going to go over my working one more time. So that gives us 75. So just to go over my solution one more time. So the percentage by mass of carbon in the monomer is going to be the same as the percentage by mass of carbon in the entire polymer chain. So we know that the percentage by mass of carbon is 86%. So what that means is if we can find the mass of one polymer chain, then we can find the mass of carbon in that chain. And if we know the mass of carbon in the chain, we can find the moles of carbon in the chain. And if we know the moles of carbon in the chain, we can find the number of atoms using Avogadro's number. Okay, so sorry about that one, guys. That one got me a bit. But yeah, so the thing to take away from this one is you can use Avogadro's number to calculate the amount of atoms that are in a particular polymer. Okay, so let's have a bit of question time before we move on to the final module. If anyone has any questions about what we've done so far, any more general questions, if you guys want to ask it, feel free to shoot now, otherwise we'll move on. Doesn't seem like we've got any questions. So could you read that out? Here we go. So someone's asking if we had just done the percentage of the carbon divided by the total molar mass. Yeah, so someone's saying that if we had the percentage of carbon divided by the molar mass, then that would give us the correct solution. Which I'm not, let me think if that's correct. I'm not sure, I'd have to work it out. It's possible, it's definitely possible. The way I did it works though, that way might work as well. We don't have any more questions, do we, Emma?
No, I think that's everything.
Okay, lovely. Well, let's move on. So this is another, so yes, we're into our last module now. So this is an atomic absorption spectroscopy question. And once again, this is a really long one, which often gets people. So I'd love it if you guys could read through it and maybe, so don't answer the question because it would take too long to like if everyone just does it themselves, but please read through it for me and think about a sort of method that you might use to do it, which is similar to the titration one we were looking at earlier. So I'll give you a couple minutes to do that.
Okay, I think you're ready to go, Jackson.
Okay, cool. So let's start by just sort of making a small diagram of what's going on in this question. So as I was saying before, sort of writing out the steps in the question can be really helpful to help you understand it. Okay, so we're trying to talk about, we're trying to find the percentage by mass of manganese. in a 12-gram sample. So we have the still sample is first dissolved in nitric acid, and the Mn2+ ions were oxidized according to the following equation. Okay, so the important thing about this equation is that the amount of moles of manganese that are in the reaction is going to be the same as the amount of moles of permanganate. So what that means is if we can find the moles of permanganate, then that's going to be the same as the moles of manganese. So that's going to be the same. So like the important thing about that is we don't need to do any calculations to work backwards from permanganate into manganese. Okay, so what we're essentially saying here is if we can find the moles of permanganate, then we actually know the moles of manganese and we can find the mass of manganese from that. So I'm just sort of like getting an idea of the method that we're going to use. So after that, so we have our permanganate. The permanganate, like that, that is made up to a volume of 1 liter. So there's 1 liter, and then 20 milliliters of solution are taken out. So 20 milliliters taken out, and then that's diluted to 100 milliliters. So I think just sketching out a quick little diagram like this can be really helpful with these questions. All right, so then as I was saying, these longer style questions, it's great to start from the end and work backwards. So if we're starting from the end, we have this 100 milliliter solution which contains some permanganate, and we're saying that the absorbance is 525 nanometers. The absorption at 525 nanometers was 0.5. So the way we use these calibration curves is we see what the absorption is, which is 0.5. We go along, and then we use that to find what the concentration is. So, these calibration curves, basically you just use them to find a particular concentration, which in this case is just 35 milligrams per liter. So you'll notice that the units are milligram per liter. And then once you found that concentration, you don't need to worry about the calibration curve anymore. Okay, so we know that in this 100 milliliter sample, we have 35 milligrams per liter of permanganate. Okay, so from there, we're going to work backwards. And remember, we're trying to find the mass of manganese. So if we work backwards, we have 100 milliliters. So what that means is that at this stage, we have so like we know there's 35 milligrams in a liter, but we only have 100 milliliters. So it's going to be a tenth of 3.5 milligrams. So it's going to be 3.5 milligrams of permanganate in this 100 milliliter sample. So hopefully that makes sense. So if we know there's 35 milligrams per liter in the sample using the calibration curve, then that means that there's 3.5 milligrams in 100 milliliters. And then we know that a 20 milliliter sample was previously diluted. However, dilutions, they don't actually change the mass of the thing that we're talking about. So if you just add like 80 milliliters of water to 20 milliliters of solution which contains permanganate, that's not really going to change the amount of permanganate, right? So we know that at this stage, there's also 3.5 milligrams of permanganate. So in these questions, it's helpful to sort of work in mass or moles instead of concentration, because mass or moles, they're resistant to dilutions. So what that means is if you ever dilute or take part of something, it's a lot easier to work with. So that's a general tip for these questions. So what we know is that in the earlier step, we had 20 milliliters taken out. So this is another reason that working with mass is helpful, because if we know that 20 milliliters is taken out of a 1 liter sample, we know that there must be so 20 milliliters goes into 1 liter 50 times. because 50 times 20 is 1,000. So 20 milliliters times 50 is 1 liter. So what that means is there must be 50 times the amount of permanganate in the 1 liter solution as there is in the 20 milliliter solution, because you're just like taking part of the solution out. So what we can say therefore is that the amount of the mass of permanganate in this 1 liter is 3.5 times 50, because there's 50 times as much permanganate in the 1 liter. So we're going to do, so 35 times 50 is 175 milligrams. Is that right? Let me put it into my calculator. 50 times 3.5. Cool, 175 milligrams. So now we know how much permanganate there was in that 1 liter. Cool. So if we then, so we're still working backwards here. So from this equation, remember, we know that the moles of permanganate is going to be the same as the moles of manganese. So let's work out the moles of permanganate to then give us the moles of manganese, which is what we're trying to find. So we know the mass of permanganate, which is 175. So moles equals mass over molar mass. So we know therefore the moles of manganese is going to equal 175, but it's in milligrams. So we're going to have to do 0.175 because we always got to use our SI units. And we're going to divide that by the molar mass of permanganate. So I'm just going to have to use my periodic table. So the oxygen is going to contribute 4 times 16 to the molar mass, and then the manganese. I just need to put my periodic table to find the molar mass of manganese. Give me a second to find it here. Okay, 54.94. 54.94. So 54.94. So that's going to be the mass of permanganate. So I'm saying that this is the moles of manganese because the moles of manganese is going to be the same as the moles of permanganate, which is what we're working out. So yeah, so I'm going to put that into my calculator now to get the moles of manganese. 0.175 over 4 times 16 plus 54.94. And that's going to be 0.00147 moles. And from that, we can find the mass of manganese, because remember, going back to the actual question, we're trying to find the percentage by mass of manganese in the steel sample. So we know that the steel sample is 12 grams, and we can work out the mass of manganese now. So the mass is going to be moles times molar mass. So 0.00147 times the molar mass, which is 54.94, which equals 0.08. So therefore we can divide 0.08 by 12 to get our answer for this question. Okay. So with these questions, once again, I just want to reiterate that sort of method. So I think that writing out each of the steps is really important. And then just thinking about what happens at each of the steps is really important as well. So just feel free to write a diagram, make sure you're working all the right units. And when you're working backwards like that, work in mass or moles instead of concentration, because as we saw, if you're ever diluting stuff or taking stuff out, then you can do a lot more easily with mass and moles than mole mass. All right. So here we go. So this is just a little intro question. So we're about to look at some organic spectroscopy stuff. So if you guys would give this a shot for me and then post your answers, just to get us into the headspace of like HNMR, CNMR, that sort of stuff. So if you could put a poll up for me, Emma, that would be great. Thank you. right, so the majority of people thought A, couple thought B or C. All right. So with this one, let's start by drawing it out. So propan-2-ol looks like this. Okay, so a hydrogen environment. So like the first thing to say is that all the hydrogens connected to one carbon, they're all going to be in the same environment no matter what. So essentially, when you're considering hydrogen environments, you're also considering carbon environments, basically. So like if multiple hydrogens are connected to something, they're all part of the same environment. Great. So an environment is like basically how it works, like visually, is if things are the same distance away from every other atom in the molecule, then they're in the same environment. So in this question, you notice all of these hydrogens and all of these hydrogens, they're the same distance away from every other atom in the molecule. Because it's symmetrical, like this hydrogen and this hydrogen, they're both experiencing symmetrical sort of pulls from every other atom in the molecule, and that's how HNMR works. So basically, stuff that is closer or less close to other atoms in the molecule experience different pulls from the spectroscopy. Okay, so if these are the same environment, then we're only left with this hydrogen and this hydrogen. So therefore, we're going to have 3 hydrogen environments. Great. So I thought I'd just go over that. And the carbon environments work really similarly. And so now what we're going to do is we're going to go through a longer spectroscopy question. So I've got all the spectra here from a particular compound that we're trying to identify. And I'd love to just go through with you guys my method for identifying these compounds, because in harder questions, you've got to have a really particular method. So with these questions, identifying the molecule or the organic compound is only half the battle. So if it's like a 5 or 6 marker plus, then they won't give you full marks if you just identify the compound. Most of the marks in these questions come from how well you sort of explain your thought process for identifying the compound. So more than anything, I'd like for you guys to take note of sort of the way we move through this question. And the way we move through it, it's sort of going to be like an investigation. So like we were doing with that organic question before, what we want to do is we want to have a bunch of organic compounds that we're considering that might fit the criteria that we've seen so far. And along the way, we're going to slowly cross each of them off. And like phrasing your answer that way is a good way to go. So from the mass spectra, the biggest thing we can take away from the mass spectra is the rightmost peak gives us the molar mass of the compound. So that's a really important idea. So these peaks also can be used, but what I'm going to do is I'm going to start by working with the most important pieces of information. And then as I go through, I'm going to slowly get down and talk about like the more niche pieces of information, because this information like molar mass is going to rule out a lot more compounds than the rest of the information in this spectra. So from this diagram, we know that the molar mass of the compound that we're looking at is 88. And a great thing to do at this stage in the question as well is to work out roughly how many sort of mid-sized molecules we're looking for. So by mid-size, I mean like lots of these compounds include like carbon, nitrogen, and oxygen, right? These are our sort of mid-sized atoms. There are lots of the things include. So I'm saying like we're going to ignore the hydrogens for the moment. So if we say that these all weigh like around, let's say 15, what we should do is we should divide 88 by 15 to just give like a rough estimate of how many. So 88 divided by 15 is almost 6. So we're going to say that like the amount of mid-sized particles that we can expect from this organic compound is going to be around 6. Maybe it's 5, 6, or 7, depending on how many hydrogens there are. But like the reason this is helpful is because then we can sort of like, we can get an idea of how big the compound's going to be. All right, so that's what we'll take from the mass spectra. If we need some more information later, we could come back to it. The next thing you should look at in these questions is definitely the IR spectra. So the IR spectrum, it helps us identify functional groups in a compound. So this is what's called the fingerprint region of the infrared. And the fingerprint region is always a bit choppy. So you will have some peaks in there that you're going to sort of ignore. However, a peak that looks this big, we're probably not going to ignore. Also, a peak that's this big, we're not going to ignore. So what you do in this one is you look for like the significant peaks. You use your formula sheet then to find like what functional group that impression is representing. So I'd love if you guys could open a new tab and get up a formula sheet of your own, or if you have one handy, that'd be great too, just so you can follow along at the same time. So if you just search up like NESA chemistry formula sheet, you can find a formula sheet, just because, you know, like for these questions, the formula sheet's really imperative. So I'll give you guys a second to do that. And then, so I've got a formula sheet in front of me as well. So if you go to the section which says infrared absorption data, you'll find that a particular bond or a particular functional group correlates to a specific wavelength in the IR spectrum. So if we're looking at sort of like the most significant impressions, our most significant impressions are at like around 17 to 1800 and around 1200 to 1300. So if we go to our formula sheet, in that range, a C double O bond looks very likely. And also a CO bond looks very likely. So if you go to your formula sheet and you go to infrared absorption data, you'll see that the peaks that we can see on this spectrum correlate to a C double O bond and also a CO bond. So you should go through and check the other peaks here to make sure that they're not sort of correlating to anything. You might be a bit confused about this leftmost peak. So you'll see that this is in the range. Sorry if my thing works. This is in the range that acids and alcohols are usually at. However, you do have to memorize that alcohols roughly look like this. So that they're sort of thin and they've got like, they almost look like a parabola or something, like they're sort of nice. And then acids are wider, like acid functional groups look a bit wider like that. So they're a bit more like, you know, thick. So this here isn't representative of an acid or an alcohol, in case that was confusing. Okay, so by this point, we can be pretty sure that the compound that we're after is going to have a C double O bond. It's also going to have a CO bond. And although we could technically have a molecule which has these in different spots, it seems likely that we're going to be talking about an ester at this point. So this is like our classic, you know, like this is the ester functional group, right? And if we have a C double O bond and a CO bond, it's pretty likely that we're going to be looking at ester. And from here, let's think about the molar mass again. So we know that our molar mass was 88. And so far, we've taken up 12 plus 16 plus 16, which is 32 plus 12, 44. So we've taken up 44 of like 44 molar mass away from the 88. So what's left, like we have about 44 weight to make up with the remaining atoms in this compound. So at this point, I think it's good to start drawing some potential candidates. So we could have like this sort of thing. We could have carbons on the other side. So we're thinking we're going to have probably 3 carbons other than this to make up the molar mass. So we could have carbons on this side, we could have carbons on this side, but we're probably just going to have 3 apart from this initial functional group. Excuse me. All right, so from the IR spectrum, the big thing that we've learned is that we're probably looking at ester. Now let's go to the CNMR spectrum. So what we have here is 4 unique carbon environments. So what we want is we're going to have at least 4 carbons then. So in this question, that sort of fits in with what we were thinking already, right? Like we were probably thinking that we're going to have 3 other carbons other than this one to make up the molar mass. So let's say that this is a candidate. So at this point, I'm definitely going to write down some potential candidates. So this is a candidate. I might write them a bit smaller actually, just so we can fit them all in. And then as with that question we were looking at earlier, as we sort of move through candidates, I'm going to cross out ones that don't make any sense. This is one. This is also one. This is one. This is one. And I think that that's all the ones that we can think about at this point. So you might ask, like, how do we know that there's not going to be any branching? So for example, like, why couldn't this be a candidate? And this should definitely be something that you should consider. You should consider, is there branching? So what I mean is like a weird methyl group or something. And the reason that this isn't going to be the case is because if we had this, there would only be there'd only be 3 carbon environments, because these 2 would share the same environment because they're both equal distances away from everything else in the molecule. Okay, so in other questions, let's say that there were only 3 carbon environments on this spectrum. In that case, we then consider that there's probably some branching. But in this case, we can be pretty sure that we're looking at one of these 4 molecules. And by the way, like, let's imagine you're writing out your response as you're doing this. You would definitely want to say this. You'd want to say, like, after looking at the CNMR spectrum, we can be pretty sure that our 4 candidates are butanoate, methyl propanoate, ethyl ethanoate, or propyl methanoate. And you definitely want to say that. And then literally as you go through, you'll be like, this piece of information discounts this compound. So in lots of the marking schemes for this question, they do give marks for discounting molecules that look like the correct answer. So in your answer, you do definitely need to say why it can't be other stuff. So this idea of like funneling down potential organic compounds is definitely one to use, like, when you're thinking about it, and also when you're writing out your response. All right, so let's go on to the next one. So this is our HNMR spectrum. And in this one, you'll notice that we have only 3 impressions on the HNMR spectrum. So at this point, like, you would have sort of thought that there would be, there'd be 4, right? But there's 3. So if we go through each of these, like, this would have, this molecule here would have 3 hydrogen environments, because this carbon wouldn't have any hydrogens, whereas the others would have hydrogens. And all of the hydrogens connected to the carbons in this one, I'm just talking about this second one at the moment, they would all be differently spaced from all the other atoms in the molecule. So therefore, based on just like how many peaks there are, this second one sort of fits the criteria. And if we look at all of them, actually, all of these compounds that we've drawn so far, they would all have 3 unique hydrogen environments. So this HNMR spectrum, just looking at how many big peaks there are, isn't going to help us rule anything out. So looking at the HNMR, why don't we talk about the splitting instead? So this splitting is really important. So you can use the splitting to find out how many hydrogens they're going to be on the adjacent carbons. This is a really important rule. So the amount of splits in a particular peak, if you subtract 1 from that, you find the amount of hydrogens on adjacent carbons. So for example, this has 4 splits. So this big peak, it represents 1 hydrogen environment. So it represents a hydrogen environment, and the hydrogen environment that it represents is going to be adjacent to 3 hydrogens. That's how it works. So for example, with this one, this is representing a hydrogen environment, which is adjacent to 2 hydrogens. Okay, so what we need, like based on this, if we go through each of the compounds, like we're expecting one that is adjacent to 3, one that's adjacent to none, and also one that's adjacent to 2. So if we go through them, we can narrow it down. Like if we consider this one, this has a carbon. So if we draw in our hydrogens for this guy, if we draw in our hydrogens for this guy, you'll notice that this hydrogen environment on the middle, this is actually adjacent to 5 hydrogens. Because there's 5 hydrogens, you know, like there's 1, 2, 3, 4, 5. So what that means is that we can discount this compound because it has a hydrogen environment which is adjacent to 5 hydrogens. But what we're seeing from the HNMR spectrum is that like we don't have any hydrogen environments like that in reality. So let's go through. If we look at this one, this compound has, like, if we draw in all the hydrogens, like this, it has a hydrogen environment, which is adjacent to no hydrogens, which is what we want. It has a hydrogen environment, which is adjacent to 3 hydrogens, which is also what we want. And it also has a hydrogen environment that is adjacent to 2 hydrogens, which is this one. So this compound so far fits the bill. We can also rule out this compound in the same way that we ruled out the first one that we ruled out, because it has a carbon, which is a hydrogen environment, which is adjacent to 5 hydrogens. Okay, so we're almost out of time. So I just want to quickly sum up this question. So we've gone down to 2 options, right? The final step in this question is to look at the CNMR spectrum, and we have chemical shift data. So this chemical shift data, like based on how far it is, so like based on this horizontal scale, you can go to your formula sheet. So for example, this peak, this is at like 170, right? So if you go to your formula sheet and you look at the CNMR chemical shift data and you look in the 170 section, you'll see that in the range of 160 to 185, you have an ester or an acid group. So the CNMR chemical shift data, it tells you some idea about what the bonding looks like within the molecule based on how shifted it is. And I just love to get some of you guys' questions before we go. So I'm going to leave it there. But if you use that chemical shift data, the answer becomes obvious. So I'll leave it for you guys to figure out yourselves. It's a little exercise. So see if you can use the chemical shift data for this to figure it out if you'd like to. Otherwise, why don't we quickly open it up for any questions? Do you guys have any questions about what we've talked about in that last bit, or any questions to sum up? I'd love to hear, you know, anything else I can help you guys out with, or is that all from you guys? Okay, cool. Seems like that's about it. Well, so if you guys like to have some more sessions like this, you can click on this QR code. But yeah, otherwise that's about all. Is that all, Emma, that you have?
Yeah, thanks everyone so much for coming, and we'll just end the meeting here. We'll send an email after and you'll get a link to the recording if you want to watch any of this back. Okay, awesome. Thank you guys. Bye.
Thanks, Emma.